activity of certain group of reagents, they can be controlled by changing the reaction conditions. So this is why the reactivity of the selectivity of certain reagents, they help in identification of a wide range of materials. So gravimetric technique, they may be more accurate than an instrumental method which requires calibration or standardization. So instruments generally, they provide relative values and they have to be calibrated first on the basis of either the results of the gravimetry or volumetric methods. So we know that the gravimetric methods are more accurate than those that we than the results that we obtain from normal instrumental analysis. So before understanding gravimetric processes, we will first understand two terms. The one is supersaturation and another is nucleation. So coming to nucleation, it is a physical reaction which occurs when components in a solution, they start to get precipitated. So like one of the common examples of nucleation is supersaturated sugar water. We know it is used to make sugar candy or the rock candy. So here the sugar crystals, they nucleate, they come together and they grow into crystals. So before understanding nucleation, we should know about the dependence of solubility on the particle size. So now we know the solubility of a substance at a given temperature in a particular substance, a solvent, is the amount of substance that is dissolved by a known weight of the solvent when the substance is in equilibrium with the solvent. So this means that the for any particle size, let us consider the particle size is less than 0.01 mm, then the solubility increases greatly with the decreasing the particle size. So in gravimetric analysis, the larger particle size, they form precipitates and they are less prone to surface adsorption, they are easy to filter and they can be washed properly. So it is always important to remember that those particles having larger sizes, they form precipitates. So the particle So now coming to supersaturation. So here supersaturation, as nucleation is one process, supersaturation is also another process. So what happens in supersaturation? It is that it is a supersaturated solution is one which contains greater concentration of the solute than that is actually permitted at a particular temperature. So supersaturation means a saturated solutions which can accommodate more solute molecules. So supersaturation is an unstable state just before the precipitation begins. Now this unstable state, it may be brought to equilibrium by addition of a crystal of the solute or some other substance by mechanical shaking. Then coming to rate of precipitation, the first person to study the relationship between the size of a particle of a precipitate and the rate of precipitation was von Wiemann. He first studied this. He proposed that the initial rate of precipitation is proportional to relative supersaturation. So that is, the initial velocity of precipitation is directly proportional to Q minus S by S. to this quantity. So here Q is the concentration of a species at any instant, and S is the equilibrium solubility. So here this equation, or this initial velocity of precipitation, was found to be directly proportional to this quantity, and this was proposed by Van Wieman. Then this Q minus S, it represents the degree of supersaturation at the moment precipitation begins. So the larger this term, then the greater is the number of nuclei and smaller is the size of the particulate. So here the term S, it represents the factor that opposes the precipitation. The greater the value of the S, the smaller is the ratio, and hence smaller number of nuclei is formed. So when Q minus S by S is low value, then when Q is small or increasing, S is large. So a moderate decrease in Q can be made by using dilute solution and adding the precipitating reagent very slowly. However, this S can be increased by using some of the factors such as temperature, pH, etc. So this S can be increased by precipitation is usually carried in hot solutions because the temperature is high and the solubility, it increases with temperature. So it is generally recommended to carry precipitation from dilute solutions, and the reagent is added slowly with constant stirring. The slow addition of these reagents, it helps in the formation of primary particles which grow as precipitates. Now, in order to increase the solubility, the addition of a suitable reagent is often recommended. So this also leads to formation of larger particles or precipitates. Then coming to digestion of the precipitate with the mother liquor. So in order to improve the nature of the precipitate, the above approaches are adopted during the actual precipitation processes. However, there is one other recourse available after the precipitation. So what is that? The material of smaller particles that can also go into the solution and reappears on the bigger particles and make them further larger in size. So this is achieved by digesting or aging the precipitate. So what does this digesting or aging the precipitate means? It amounts to the fact that if the precipitate is allowed to stand in contact with the mother liquor for some time at an elevated temperature, then some of the particles before filtration, the smaller particles, they go into the solution, making it super saturated. Then the equilibrium with respect to the larger particles is achieved when the material leaves the solution. So this additional materials, it appears as larger materials, and this process is called as Ostwald ripening. It has been found that digestion does not significantly improve the nature of curdy precipitate like AgCl or FeOH3. This happens when the compound is very insoluble or the particles do not differ in size. So digestion at elevated temperatures before filtration has been successful in increasing the particle size of barium sulfate and calcium acetate, oxalate, sorry. Then coming to one process that we call it as co-precipitation. So here the precipitates that are separating out from a solution, but sometimes they contain larger amount of other unwanted materials also, including the parent solvent. So these precipitates, so these are the impurities that might be present in our original precipitate. So the contamination of the precipitate by the substance that are normally soluble under the conditions of precipitation is called as co-precipitation. So the contamination as a result of this co-precipitation, it should be distinguished from contamination as a result of chemical precipitation. So a typical example of co-precipitation is when barium chloride is added to a solution of potassium sulfate. Then the precipitate, that is the barium sulfate, is formed. After washing, it has been found to contain some amount of potassium sulfate. So this is co-precipitation. It prominently takes place by two mechanisms, that is adsorption at the surface of the particles and by occlusion of incorporating of foreign ions and the parent solvent. So then what are the methods to minimize co-precipitation? So here some of the methods have been listed below. The first is, actually there are no general rules, but some common approaches are: the precipitation should be carried out from dilute solutions, keeping in mind the solubility, the time required for filtration, and the subsequent operations to be carried out with the filtrate. If the precipitate formed by mixing very concentrated solutions at room temperature, then it separates out as a colloidal solution, so which is also prone to further contamination. The reagents, they should be mixed slowly with constant stirring. This is how we can keep the degree of supersaturation low and we can get more precipitates. Precipitation should be carried out from hot solution provided the solubility and stability of the precipitates permit. Now, since the solubility increases as degree of supersaturation increases, the coagulation of the precipitate is assisted, thereby reducing the salt formation, and the velocity of crystallization is increased, thus leading to be formed as better crystals. Then also we can minimize co-precipitation by crystalline precipitates. They should be digested with other liquid as long as they are practical. Digestion of the precipitate may be done by leaving the precipitate in contact with the mother liquor. So it should be emphasized that the digestion has little effect upon amorphous or gelatinous precipitates. We can also carry out second precipitation. Less amount of foreign substances are involved, and consequently the impurities that will be formed will be very less. So these are the 5 points that we need to be remember while carrying minimizing the co-precipitation. Now coming to role of co-precipitation in the separation of tracer quantities. Now we see that co-precipitation is actually contamination of the precipitate. So in order to obtain a pure precipitate, we have to avoid the possibility of co-precipitation. So the this co-precipitation can be, but although it is a process of contamination, but co-precipitation is very useful for the separation of tracer quantities of radioisotopes. So the radioisotopes, we know they are produced by nuclear reaction, and they are present in very minute quantities, and therefore the detection in such small quantities is very difficult. So the separation of such low amount of tracer material from macro quantities of target materials by co-precipitation, it is done, and it usually involves two steps. First, the tracer is separated and concentrated from the target material by co-precipitation. Thus, the role of the carrier here, it is to carry the tracer amounts by surface adsorption. Secondly, the tracer is separated and concentrated from the carrier material. So it is desirable to use carrier substances that can be separated from the tracer element easily in the following operations. So generally the tracers, they are co-precipitated by surface adsorption on unspecified carriers. Now this adsorption, it occurs because of the large surface that are offered to the tracer elements by the various types of material substances of high specific area, such as manganese dioxide, metal sulfates, hydrated oxides, they even ferric hydroxide, they are used for such type of carrier materials. The use of ferric hydroxide as a scavenger for the separation of barium radioisotope from cesium target has been, it shows as an example of this utility of co-precipitation. So the separation of barium from cesium, it is made by co-precipitation of barium on ferric hydroxide at pH 10. Then the separation of barium from this iron, it is made by dissolving the precipitate and again reprecipitating ferric hydroxide at pH 5.4. So here the barium, it remains in the supernatant liquid, and then we can calculate the amount of tracer amount of barium that has been present, or cesium that has been present. Then there is another technique that is called as post precipitation. So co-precipitation, we know it is, although it is a type of contamination, but this is also a useful process. There is also another process that is called as post precipitation, which makes a precipitate impure. So in this case here, as the name suggests, the primary precipitate, it first separates out in the pure form, but the second precipitate that comes out, it becomes slightly, it contains a slightly other foreign substances. That is why the second precipitate that comes out from the reaction is called as, the process is called as post precipitated. So here post precipitation can occur only when the supernatant is supersaturated with respect to some component which crystallizes fairly slowly. So this means that Now, with sparingly soluble substances which form supersaturated solution and usually have a common ion. So, in the precipitation, for example, in the precipitation of calcium oxalate, in the presence of magnesium, a small amount of calcium is co-precipitated with calcium oxalate. However, if this suspension is digested, then some magnesium oxalate appears on calcium oxalate. So this is an example of a post precipitation reaction. So another typical example of a post precipitation reaction is when H2S is passed through zero point 0.2 normal sulfuric acid solution which contains Cu2 plus ions and Zn2 plus ions. So the copper sulfide will first precipitate without carrying any zinc. So this means that there will be no co-precipitation. However, if the precipitated copper sulfide is left with zinc ions in solution containing zinc sulfide, then it is precipitated at the copper sulfide precipitate. So this is called as the post precipitation reaction. Now, coming to some of the differences in co-precipitation and post-precipitation reactions. The major point of differences are: number one, if the precipitate is left in contact with the parent liquor, then the contamination increases with time in post-precipitation. But the contamination increases the faster the solution is agitated if we stir it mechanically. So the reverse is generally the case with co-precipitation. In case of post precipitation, the contamination increases the faster the solution is agitated. But here it does not happen. The magnitude of contamination of by post precipitation, it is much higher than that by co-precipitation. So these are some of the points of differences between these two methods. Now we will talk about the precipitation from homogeneous solution. So one of the major objectives of the precipitation reaction is the separation of a pure solid phase. Now, in order to obtain a pure solid phase with well-defined crystals, so we need the contamination to be as much low as possible. So here, that is, in other words, a compact and dense precipitate instead of a gelatinous precipitate is what we always want. So here there are certain guidelines that need to be followed to obtain a compact precipitate. The key lies in the fact that the degree of saturation should be kept minimum. So this will lead to fewer nuclei and the material will grow on them. So ideally, the precipitating reagent should be added in small successive amounts until its concentration just reaches the saturation value. So, but the ideal rate is rarely attained in a direct precipitation process. This problem has been sorted out by slowly generating the precipitant by a homogeneous chemical reaction within the solution instead of adding an externally. So this technique is known as homogeneous precipitation. So different types of approaches have been adopted to carry out homogeneous precipitation. So they are classified into four different categories. The first is generating the precipitating anions by slowly hydrolyzing the ester or some suitable compounds. The second is the raising the pH of the solution. Third is synthesizing reagents within the solution by reacting different reagents. And the fourth is releasing the cation slowly by changing its oxidation state or by destroying its complex. Now coming to generating anions by hydrolysis. So anions have been generated in solution to precipitate different types of insoluble salts, like for example precipitates of phosphates. So phosphates are insoluble and they can be precipitated with phosphate that are generated from triethyl phosphate or metaphosphoric acid. This is metaphosphoric acid and here it generates a phosphate, so which are insoluble. Similarly, the esters of oxalic acid, they can serve as a source for oxalate ion. So here we get oxalate ion and they are can also precipitate as oxalates. So then coming to precipitate of sulfate. So when we do the hydrolysis of sulfamic acid, it serves as a method for generation of sulfate ions. And we know this sulfate ions, either barium sulfate or lead sulfate, they are insoluble in water, and this reaction, that is used for separation and determination of barium ions. So hydrolysis of diethyl sulfate has been used to precipitate calcium, strontium, barium, and lead sulfates. These are some of the examples. Then coming to precipitates of halides. So many sulfur containing compounds, they undergo hydrolysis to form sulfide ions, but thioestamide, that is CH3CsNH2, it has been more popular and it undergoes hydrolysis to form the sulfide ions here. And here the detection of antimony, bismuth, molybdenum, copper, arsenic, lead, cadmium, tin, and mercury has been performed by this method. So this is how the precipitates are formed and they can be quantified. Then coming to synthesizing reagents by reaction of different compounds. So when one of the major drawbacks for precipitation reaction is the use of organic reagents which determine the nature of the precipitates. So most of the precipitates that are obtained by organic reagents, they are flocculent in nature. So in view of certain advantages of organic reagents, there has to be so one of the methods has been synthesize the reagents in situ during the reaction. So one best example is by the precipitation of Ni2 plus by synthesizing dimethyl glyoxime by the reaction between biacetyl and hydroxylamine. So this biacetyl, it reacts with hydroxylamine to form the DMG, that is dimethyl glyoxime. This dimethyl glyoxime, it readily reacts with nickel, forming nickel dimethyl glyoxime, which precipitates out. Now, another well-known reagent is salicylyl oxide, which is used for precipitation of copper. Now, this is generated by reacting salicylaldehyde with hydroxylamine, which forms the salicylyl oxide, and it reacts with copper, forming the in precipitate. So the cupeferon has been synthesized in situ by the reaction between nitrate and phenyl hydroxylamine to form insoluble precipitates of chelates of copper, iron, and titanium. Here, this has been shown. Phenyl hydroxylamine, it forms this compound which reacts the action of nitrous acid with 2 naphthol led to slow precipitation of cobalt 1 nitroso 2 naphthol. Here example has been given here. So there are various such types of examples where the reagent is generated into during the reaction and it has been used for estimation of the insoluble precipitate of metal precipitates. Then coming to washing of the precipitate. So when we obtain a precipitate, then it is important that the washing is done, else it might contain impurities which are not required for us. So the object of washing the precipitate is to remove the impurities containing the precipitate as completely as possible. So here, but when we wash the precipitate, only the surface impurities are removed. This means that under optimum conditions, the washed liquid just removes mechanically, it removes the impurities which are very loosely bound to the precipitate. So which are strongly, the impurities which are very strongly adsorbed by the precipitate, they must be washed with certain chemical reagents. That is why the composition of the washed liquid is very important. Moreover, these washed liquids, they must be chosen carefully so that they do not react with our precipitates. The precipitates which have significant solubility in water may be washed with water containing a common ion to the precipitate. So typical example that is taken is calcium oxalate. Like calcium oxalate is washed with an aqueous solution of ammonium oxalate. So what happens here is the dissolved constituent, it should be volatile. If the precipitate it is somewhat soluble in water, then it may be washed with water alcohol mixture. So for washing lead sulfate precipitate, either dilute sulfuric acid or 50% aqueous ethanol might be used. Some of the precipitates, they have a tendency to become colloidal and pass through the filter paper. before passing through the filter paper. Such a tendency is observed when with gelatinous precipitates. Now, the process of peptization is rare with well-defined crystal precipitate. Now, when for washing precipitates which peptize, then the wash solution it should contain an electrolyte. And for this process, hydrous ferrox oxide it is washed with dilute ammonium nitrate solution and silver chloride precipitate with 1% HNO3. Now, there are other precipitates which tend to oxidize during the washing process, and such precipitates cannot be allowed to dry. So, in order to prevent this problem, then the precipitate should be washed with a special solution which reconverts the oxidized product into the original one. So, like for example, copper 2 plus is not gravimetrically determined as sulfate, but it is a known of separation of copper. The CuS precipitate which is formed it has a tendency to oxidize to copper sulfate and should be washed with acidated hydrogen sulfide water. So these are some of the methods by for washing a precipitate. The chemical composition is important and the nature of the precipitate is also important. So how this is how we should identify the reagents for washing the precipitate. Now, if the precipitate is a salt of a weak acid or a weak base, then it should be washed with a solution which prevents hydrolysis. For example, if the precipitate is a salt of a weak acid and is it lightly soluble, it may show a tend to hydrolyze and the soluble product of the hydrolysis will be a base. So in such a case, the washed liquid should be a base. So like we take the case of magnesium ammonium phosphate, which hydrolyzes to give hydrogen phosphate ion and the hydroxide ion. So thus it should be washed with aqueous ammonia. So but if we take the salts of a weak base such as hydrated ferric, chromic or aluminium ion, then the washing may be done with silica or by maybe hydrolyzed to their basic salts and hydroxides and acids. So the addition of an acid to the wash solution it will prevent hydrolysis of ferric or similar salts. So thus we can, in summary, we can say that the wash solution should have the following characteristics. Number one, it should not have any dissolution action upon the precipitate but just remove the impurities only. It should not peptize the precipitate. It should not form any volatile or insoluble product with the precipitate. It should be easily volatile at the temperature of drying of the precipitate. And number five, it should not contain any substance which is likely to interfere with the determinations in the filtrate. Now, during washing of the precipitate, the following general procedure protocols that are followed are: number one, since no precipitate is absolutely insoluble, the minimum volume of the washing liquid required to remove the objectionable material it should be used. It is better to wash the precipitate with small portions rather than one or large two portions. And thirdly, the wash liquid should be well drained between each washings rather than adding fresh portion of the washing while the solution still remains on the filter. So these are the some of the protocols that we need to follow while washing a precipitate. Then coming to organic precipitants, their advantages and their disadvantages. So in the previous section, we talked about the different types of precipitates. Here we will talk about particularly about organic precipitants. So the applications of organic precipitants are huge. They are as a titrant, indicator, colorimetric. So they also form some major applications in analytical methods. So one of the major applications is the use of organic reagents as precipitating agents. So separation of one or more ions from mixtures can be made with the aid of organic reagents because they form colored compounds. So these organic compounds they have high molecular weight and they give a large amount of the precipitate with a small amount of the metal ion. So as a result, the sensitivity of the procedure is increased. So as the yield is increased, the sensitivity of the reaction it increases. But what happens is Ideally, the organic precipitant should be specific, that is, it should give a precipitate one with one particular ion, but sometimes it is difficult to attain this situation. However, it is usual that a organic reagent will react with a group of ions, and frequently by rigorous control of experimental control. The selectivity is often greatly enhanced by the control of pH and the concentration of the masking agents. So the masking agents, they form a more stable complex with the interfering cation than that with the precipitating cation. So the interfering cation, thus it remains in the solution. Sometimes the precipitates that are obtained by organic reagents, they may be weighed after drying at a suitable temperature. So, however, in certain cases, a titrimetric method is adopted to dissolve after dissolving the quantitatively precipitated metal complex. So, now we will talk about the different types of classification of chemical reactions that have been identified with organic reagents. So, first is the formation of chelate compounds. Now we know chelate compounds are the compounds that have a ring-like structure. So here will form the largest number of recorded cases of precipitation by organic compounds. It involves the formation of unionized chelate complexes. So most of the organic compounds which form chelates with metal ions, they contain both an acidic group and a basic functional group. So the metal ion that interacts with both of these acidic and basic groups and becomes a part of the ring, that is the heterocyclic ring. So one of the examples of this class is 8-hydroxyquinoline. It is also called as 8-quinolinol or oxime. So it forms insoluble complexes with a number of metal ions. So as the insoluble complexes are formed, different heterocyclic rings can be obtained when we can use different types of metals. Then coming to formation of salt-like compounds. The organic reagents, they also form salt-like compounds of low solubility with certain cations. Like the sodium salt of tetraphenyl boron precipitates the potassium ion. So here this is tetraphenyl boron sodium salt plus K plus. It giving rise to tetraphenyl boron potassium plus Na plus. Now this salt, this is a precipitate. So here it remains as a precipitate in solution. Even mandelic acids has been known to precipitate zirconium. So this is how salt first like compounds or they precipitate using this organic precipitants. Then formation of adsorption complexes or lakes of indefinite composition. So the lake appears to be formed when an organic reagent and the hydrated oxide of a metal. So the nature is exactly not known. The combination seems to takes place on the surface of the colloidal particles of the oxide, resulting in most of the cases in the formation of a typical color. So there are many application of this lake formation in colorimetric analysis because here a color is formed. So the application mostly lies in colorimetric analysis. So like for example, tannin has been found useful in the precipitation of many metallic hydroxides. Even cinchonine, it promotes complete precipitation of hydrated tungstic oxide. So this is how lake complexes, they help in the identification or precipitation process. Then coming to reduction to the metal, some of the organic reagents, they have been used for the reduction of noble metals like platinum and gold. So hydroquinone and certain related compounds, they have been used for the reduction and determination of gold. So this is one application. And then coming to the use in homogeneous precipitation, the use of different organic reagents in homogeneous precipitation has been cited. We know urea is a familiar example which help raises the pH by slow hydrolysis to precipitate metal hydroxoxides and basic salts. So gradual hydrolysis of corresponding esters, it lead to the precipitation of phosphates, sulfates and oxalates. Thioestamide is a convenient and inoffensive source to produce H2S, which gives larger particles of different metal sulfides. So now if we go through the list of the organic reagents employed for gravimetric work, a majority of the reagents they belong to the first of the two mentioned categories. It is now, however, it is difficult to actually classify the organic precipitants. A majority of them are characterized by certain functional groups which are responsible for precipitation. Now, although we know that organic precipitants they contain different functional groups, so their actual classification becomes difficult. But we will consider the different organic functional groups which help them in the precipitation processes. So there are a number of reagents with having specific functional groups, and we will discuss one by one. So first is dioxide. We know one of the most familiar examples of a metal chelate of this category is the red precipitate that obtained in slightly alkaline medium by addition of dimethyl glyoxime ion to nickel. So when Ni2 plus is made to react with DMG, that is dimethyl glyoxime, then in slightly neutral or slightly acidic medium, then a red color complex is formed. Now this is the probably the first chelate that has been used for analytical purposes. Now sometimes palladium has been used, but the selectivity of the reaction is attributed to its configuration. So here if we look, the structure of dimethyl glyoxime looks like this. So many other alpha dioxines such as furyl dioxime 2, benzyl dioxine, cyclohexane 1,2 dioxine, and several other reagents have been known to give such type of reactions. Here the structure for all these alpha dioxines have been shown in figure 1, 2 and 3. Now orthobenzoquinone dioxide however does not precipitate nickel, so that the carbon atom in the dioxime configuration they cannot form a part of the aromatic ring without the group losing its reactivity. Even the reagent cyclohexane 1,2 dione dioxime, it is a more sensitive reagent for gravimetric determination of nickel. It is more soluble in water and possesses a more favorable gravimetric factor. It can be used in aqueous solution and in a more acidic range. Its use is restricted. Why dimethyl glyoxime is preferred for detection of nickel? It is because it is the the cyclohexane 1,2 dioxime, the reagent, it is very expensive, and there are certain impurities that follow after the precipitation process. That is why for nickel determination, the DMG, that is dimethyl glyoxime, is mostly preferred. Then coming to different nitroso compounds. There are two well-known derivatives of nitrosohydroxylamine that are cupeferon and neocupeferon. So cupeferon are ammonium salt of phenyl nitrosohydroxylamine. Here they are ammonium salt of phenyl nitrosohydroxylamine, and neocupeferon they are the ammonium salt of naphthyl and nitrosyl hydroxylamine. So these are naphthyl and nitrosyl hydroxylamine. So here the reagents they have been shown in figure 4 and 5. Both of these reagents they react similarly, but the second one it forms less soluble bulkier precipitates. They form precipitates with multivalent ions such as iron, gallium, titanium, zirconium, cerium, niobium, tantalum, vanadium, and tungsten from moderately acidic solutions. From less acidic solutions, some more metal ions may be precipitated. Both these reagents they lack selectivity and therefore they are mainly used for separation processes. The precipitates formed with cupeferon are of indefinite composition. So if the metal ion that is to be determined are using this reagent, then the precipitate is to be ignited to an oxide first. So two isometric nitrosonapthols, that is alpha nitrosonaphthol and beta nitroso alpha naphthol, they are particularly known as precipitating reagents for cobalt 2. They have been suggested for the determination of Cu2 plus, palladium 2 plus, Fe3 plus, and zirconium 4 plus from slightly acidic solutions. The composition of the precipitate it seems to be doubtful, for other works. Now, other nitroso-naphthylamines have also been suggested as precipitating reagents for cobalt, nickel, and copper. So, the composition of cobalt is closer to theoretical, and so the precipitate is recommended for direct weighing after the drying process. Now, there are other amino compounds which are used for detection. Several acids, aromatic amino acids, they have been employed as gravimetric reagents. Now, anthranylic acid precipitates a number of metal ions like copper, zinc, cadmium, cobalt, and silver. So this is anthranylic acid. The structure has been given in figure 6. So the reagent in the form of its water soluble salt, it is used to precipitate metal ions. The precipitates are pure and they are easy to filter and wash. Now, because of the lack of selectivity, it is mostly used for the determination of metal ions in pure solutions. So, quinaldic here, it reacts similarly to anthranylic acid. So, these two are the aromatic amino acids that have been used for with gravimetric reagents to precipitate different types of metal ions. Then coming to sulfur compounds, a number of sulfur compounds, that is the particularly those with the sulfhydryl group, that is SH, they have been used for such as gravimetric reagents. They may include thioanilide, mercaptobenzothio mercaptobenzothiazole, phenyl thiohydantic acid, thiobarbituric acid, thiophenol, and several. But none of the reagents of this group is very popular. These are the some of the sulfur containing compounds, but however their use is very less. Then now coming to salt like compounds. There is a wide variety of reagents which form salt like compounds that can be used for gravimetric reagents for different metal identification. So it is possible to categorize them as how they have been categorized. The important ones are the list are phenyl arsenic acid and derivatives for titanium, tin, thallium, mandelic acid, derivatives for zirconium and hafnium, tetraphenyl boron sodium for K plus, Rb plus, cesium, and benzenidine for compounds sulfate and tungstate. So many other organic acids, they have been they form insoluble salts. So these salts, they are highly insoluble, and that is why they can precipitate a number of metal ions. So under these conditions, the concentration of free phenyl arsenate or the mandalate from mandelic acid, it will be too low to allow the attainment of solubility product, and that is why it helps in the precipitation of the metal ions. So these are the different types of organic reagents that can be used for gravimetric analysis of different types of metal ions. Then coming to the advantages and disadvantages of this process. So the disadvantages are primarily due to some problems which cannot be overcome. But first we'll talk about the advantages. The organic precipitants for the metal ions, they offer wide variety, and they could be without any interference. They can be used very effectively. Most of the complexes, they are very insoluble, and the metal ions that we are determining, they can be quantitatively calculated very with precision. See, good number of reagents are selective, thus they yield precipitates with only a number, particular limited number of cations. The selectivity of organic reagents can be enhanced by controlling the pH or using appropriate masking agents. The organic precipitants, they have a high molecular weight and yield a large amount of precipitate. So once we get large amount of precipitate, the chances for error becomes very low. Then a number of organic reagents, they yield precipitates with metal ions which are coarse and bulky, and therefore they are very easy to handle for such gravimetric work. So an organic reagent with a metal ion, it may yield a precipitate which may not be suitable for weighing after drying. So this precipitate, without much problem, it can be ignited to give the corresponding oxide or the metal. So in such cases, the collected precipitate can be dissolved at the liberated organic molecule is titrated, and then we can indirectly calculate the amount of the metal ion. So these are some of the advantages of this process. Then coming to the disadvantages. So with all the advantages, the one of the fact that remains disadvantage of this process is that the use of organic reagent is very problematic, and it poses serious health risks to the person who is performing the experiment. As pointed out, the purity of these reagents is also sometimes a problem. The solutions of a number of organic reagent, it degenerates or degrades with time, so it is always required that fresh solution of the reagent has to be prepared before performing the experiment. Then several of the organic reagents have a limited aqueous solubility, and therefore there is a danger of these reagents contaminating the metal complex precipitates. So then the last disadvantage of this process is that many of the metal complexes, they do not offer a suitable weighing form of definite composition, and therefore can just be only used for separation of metal ions. So these are the disadvantages. So in summary, we can say that today we learned about gravimetric analysis and the at the macro levels. So we also major discussed about the different types of precipitation and the co-precipitation processes. We also talked about organic reagents and their utility in metal ion detection. So with this, we complete this unit. We'll just take a break of 5 minutes and then continue with the next chapter. So now we'll start with this new unit, that is Introduction to Analytical Instruments, different types of instruments. We will have a brief idea. Then in the subsequent units, in there will be full description of the instruments that you will come across. So here we will see some of the basic instruments that have been used in analytical chemistry. So first we will start with analytical instruments and their introduction. So mostly in the analytical instruments that we use, they give us an idea about the chemical composition, the what are the elements present, the amount of the elements that are present inside the complex or the material. So both quantitative and qualitative analysis can be done. So the instrumental methods and the physical properties which can be identified from these instruments that has been given in this table 1.1. So the optical properties, such as the principle is based on absorption or radiation, and the instrument is called as either photometry, spectrophotometry, or atomic absorption spectroscopy. The instrument which is based on emission of radiation, that is either flame photometry, emission spectroscopy, or fluorescence spectroscopy, which is based on scattering of radiation. This is turbidimetry, nephelometry, or sometimes Raman effect. Diffraction of radiation, one is by X-ray diffraction, electron diffraction. So the instruments which are based on electrochemical methods, such as the measurement of potential of electrode or change in potential, that is called as potentiometry. The measurement of mass of the substance which is deposited at a particular electrode, that is we call it as electrogravimetry. The change measurement of the conductivity of a substance, it is by conductimetry. Or the change in diffusion current with respect to potential, that is either voltammetry or polarography. So these are some of the instruments, analytical techniques, and their principles by which they are operated. Then we can also study the mass to change determination, that is called as by mass spectrometry, and the radioactive measurements, which are called as the radio analytical methods. So the measurement of mass is fundamental in analytical chemistry. So all measurements depend directly or indirectly on the mass of the substance. So this forms the basis of gravimetry. Now even for titrimetric measurements, the concentrations of standard solutions, they are expressed in terms of either molarity, molality, normality. But these, as we know, these three terms also include the mass. Then coming to first is an analytical balance. So a balance is the first instrument which measure the mass of a substance. So here this involves the comparison of unknown mass of an object with a known mass, and that we call it as the standard mass. So here it is defined in terms of primary standard of the mass, that is the kilogram, or when by as defined by the International Bureau of Weights and Measures in France. So in the beginning, two pan balances were used. So in this balance, the mass of the unknown was counterbalanced by the standard weights. And then we know that this weighing process in a double pan balance or a single pan balance. Then here we have colorimeter, photometer, and spectrophotometer. So here we'll start with colorimeter. So as the name implies, it is used for color analysis. So like the instrumental which can be traced to colorimetry and flame photometry analysis. Colorimetry is based on comparing the color that is produced by an unknown substance, and we will compare it to the color that is produced by the same amount of a known substance. So that is how colorimetry is done. The color of a test solution in a Nessler tube diluted to a fixed volume is compared to a series of standards of the same component prepared in a similar way. So in variation of this method, the height of the liquid is in one tube is adjusted so that when the tubes are observed vertically, the color intensities in the tubes are equal. That is we call as Dubosek method, and this is given by the relationship C1H1 is equal to C2H2, whereas H1 and H2 are the height of the test tubes, and C1 and C2 are the concentrations, one of them being is known and other is unknown. So this is how we artificial color standards, they have been chosen, such as Lovibond glasses, salt solutions of ferric chloride. These are all the standardized solutions which we consider. Then comes a photometer. So photometer currently it measures the amount of light that falls on a photocell. So they measure the light absorption by the solution that is of our interest. So basically the photometer consists of a light source, a suitable light filter to obtain an approximately monochromatic light, a glass cell to hold the solution, a photoelectric cell, and a measuring device that is mostly the detector to record the response of the photoelectric cell. So, a refinement of the photoelectric photometer, it was incorporation of two photoelectric cells instead of one. So, the example of single photocell instruments, they were the Unichem SP300 and 14 Hilger Biochem. Then the photocells, which are sensitive, light sensitive devices, they are of two types. They are called, one is the photoemissive and barrier cells. So the photoemissive cell, it is a glass tube which is coated with a thin layer of cesium oxide along with silver oxide. So they emit electrons when light falls on it, and it can be speeded up to a suitable mode. The flow of counter electrons can be measured and is related to the intensity of light that falls on the photocell. So the photomultiplier, it uses a series of positively charged anodes at increasing potentials by which the initial current can be considered to be increasing. So the cell here, so in the barrier layer cell, the voltage source is disposed of. The cell, it consists of a metal base plate of iron which is deposited over a thin layer of selenium. Now this is covered by a transparent material. So when light falls on the selenium layer, the electrons are released, so which the base plate is positive and the transparent plate is negative. Now when we connect it to a galvanometer, the current can detect with the that is proportional to the intensity of the light that is falling onto it. So in the beginning, optical filters were used in colorimeters and photometers. However, then they are using the filters were from these companies. Then coming to spectrophotometer. So in the course of time, more sophisticated instruments they came to the market. So these are refined photoelectric photometers. They use monochromatic light. Now the monochromator is an essential part of the spectrometer which is not present in a photometer. The monochromator, it splits the light into different wavelengths of the light beam. So this dispersion, the splitting is done by using a glass quartz or a prism. The prism, it shows dispersion in short wavelength than in the long wavelength. So in view of possible variations, two cell photometers they were proposed based on that fluctuations will be minimized. The most common source that is used for visible and ultraviolet and near IR region was the tungsten filament incandescent lamp, which operates at 270K to minimize the output shift. So for ultraviolet region, the best continuous region was the hydrogen discharge tube. The use of ultraviolet and visible spectrometry, it was helpful to different types of analytical methods. So spectrophotometry was developed, and today we find very advanced technologies that employs this UV visible spectrophotometer. Now coming to IR spectrophotometer. So they came into the field of analytical chemistry much later. So during 1800, William Herschel he reported that radiation existed beyond the red region of the solar spectrum, which heated up substances. But however, he was not able to understand this nature. Then uh, after 100 years later, then the first published work was regarding this region was published by Koblenz, who said that the spectres they were subsequently it was analyzed on the basis of vibrational and rotational mode of the molecules. So it becomes apparent that the spectrum represented a variable wealth of information about the basic characteristics of the molecule, the nature of the molecule, the different functional groups that are present inside the molecule. Rather, the IR is now called as the fingerprint of any molecule. So now several changes in UV visible spectrometers were necessary before IR instrumentation was possible. Parabolic mirrors, they were used to bring energy of all wavelengths to focus at one point. So both gratings and prisms, they were found useful for dispersing the energy, with a preference for prisms so as to not lose their energy. The prisms of NaCl, cesium bromide, calcium fluoride, they were found useful because these materials were soluble in water. They had to be careful, protected from humidity. Now, silicon carbide and nernst glower, which emit in the IR region, where they, when heated, they replaced the tungsten lamp of the visible spectrophotometer. Photosensitive detectors were installed in IR spectrophotometer by heat sensitive devices such as thermocouple, bolometers, Goloi thermal detector, and others. Then comes the flame photometer. So, along with comparison in solution, one of the earliest methods for detection of elements was the characteristic color of the element that emits when metals like salts like sodium chloride, KBr, were introduced. Now, depending on the nature of the color of the flame, we can identify the element that we are dealing with. So the intensity of the color of the flame was found to vary with the concentration of the substance. This was the basis of the flame photometer. So a small volume of the sample solution was sprayed into the flame in a controlled manner. Then, at a higher temperature of the flame, the water evaporated off, the salts were dissociated into constituent metal ions and atoms. So, these excited atoms, on de excitation, they emitted characteristic spectra which were dispersed using a monochromator. So, a photocell with a readout device, it measured the intensity of this emitted spectrum. So, once we know this emitted spectrum, the intensity, this was measured, and then we can, in the here the two types of built-in flame photometer has been known to us. One is the built flame photometer and another is the flame spectrophotometer. So here, in the built flame photometer, a filter is interposed between the flame and the detector that is transmitted only the high intensity spectral line. But here, flame photometers, they were generally used for analysis of sodium, potassium, lithium, and calcium. In the flame spectrophotometer, light from the burner, it passes on to the monochromator with a particular power. The isolation radiation from the element, it falls on a photocell and then it is finally detected. Now, because of the high resolution power of the monochromator, a number of other elements, they were identified. So one of the earliest commercial flame photometer was the EEL flame photometer. The flame was produced from butane or propane and compressed air. The light emitted from the flame was collected by a reflector and focused by a lens to an optical filter that is suitable for sodium, potassium, lithium, and calcium lines. The current regenerated by the photocell, it is detected by a galvanometer. So earliest example is Unicam SP900, which contained the sample compartment, the burner, the monochromator, the detector, and the galvanometer. So here acetylene was used with air to produce the flame. The sample was drawn through polythene capillary under the action of compressed air. It was fed into the atomizer and sprayed as a fine mist into the flame. So the detector is a photomultiplier tube and which can measure up to 120 nm. So here this is how an example of a flame photometer. Now coming to spectrography or spectroscopy. So spectrograph, the flame furnishes very low energy. So it results in the excitation of only a few elements. Now in order to cover more elements, other sources of excitations are the AC arc and the DC arc, or sometimes high voltages spark are used. Now, so all these arcs, they have their both pros and cons. So the sample under investigation, it was used as one of the electrodes. Otherwise, the sample was placed in a small cavity of a carbon or graphite electrode. The other electrode was of pure metal such as silver or copper. Then the optical system, it houses the monochromator. The earliest spectrograph that was built was the Hilger quartz spectrograph. The radiation emitted by the sample in the excitation source, that is the arc, it passed through a narrow slit and then it disperses the radiation into wavelengths. So here the spectrograph was provided with a scale graduate in wavelengths, and it was illuminated and printed on the spectrograph place. So for quantitative analysis, the intensity of these lines that were reflected as a black color on the photographic plate, and then they were compared with the standards. So here, besides flame and spectrographs for atomization, many other atomizers have been proposed the years. So these are indicated. So for atomizers, flame, the temperature is 1700 to 3100. Like for direct current plasma, it is 4000 degrees to 6000 degrees centigrade, and a glow discharge plasma requires a temperature of 4000 to 6000 degrees centigrade. The plasma sources, they have become one of the most widely used source for atomic emission. The advantage of the